Can I start? Wait, okay. Okay, so let's start the afternoon session. Welcome back. Good afternoon, everyone. And let us continue the two-dimensional oscillating airfoil theory in incompressible flow. So the governing equation is a Laplace equation of perturbation potential phi. And the boundary condition is shown here. It's a non-permeable condition on the blade. And this equation 2.8 is solved on the boundary condition 2.9. That is a task. But in this case, so yes, this is a singularity method. So we put the gamma A, this is bound vorticity on the blade. And due to the oscillation of the airfoil blade, the wake vortex is shed like this. So there is a vortex sheet to the infinity downstream. So the vortices exist not only on the airfoil surface, but also on the wake surface. So capital gamma is the strength of the bound vorticity on the whole airfoil. It's circulation. And circulation is expressed by this equation. So gamma A is integrated from the leading edge to the trailing edge. And, and the airfoil is assumed to execute an harmonic oscillation. So we can write the time term as exponential I omega t. So all the variables are expressed in this form. And then the boundary condition is written like this, 2.11. And the unsteady circulation, capital gamma, changes in time. And in accordance with the change, the vortices are shed from the trailing edge. So time t, we have gamma is gamma t. And at the time t plus dt, gamma is expressed as this, like this. So the first term is, only first term is retained here. And if the vortex, the strength is gamma w, wake vortex is shed from the trailing edge during the time dt, the equation 2.12, this one, is derived from Kelvin's theorem. So this is the change, temporal change of the circulation. And this is compensated with the wake vortex, shed vortex here. Okay? And as I previously said, so gamma W is not independent from the gamma A. So because gamma W is shed from gamma A. So there is a relationship between gamma A and gamma W. So since the shed vortex is transported with the uniform flow velocity, capital U, so between gamma W and gamma W at the arbitrary position in downstream field is related to the gamma W at the trailing edge here. So this is, the right-hand side is the arbitrary position X. So the gamma W at the arbitrary position in the downstream is related to the gamma W at the trailing edge with the time lag shown here. Okay. So using this relationship to equation, it's 2.12. So this is substituted into this one, so this gamma W. And we can have this relationship with capital gamma. Capital gamma contains, of course, gamma A. So gamma A and gamma W is connected through this equation. And the equation can be rewritten as 2.14. Okay? And here it's a non-dimensional parameter K emerges. So K is called reduced frequency. So this is also shown by Professor Maiti on the first day. And K is, the definition of K is, we have two definitions, depending on the chord length or half chord length, semi-chord length. So we have to be careful. So there are two kinds of K. So it's the difference in here and the double difference here. And the reduced frequency K is a parameter which expresses the level of unsteadiness. And K equals 0 denotes, it means the steady state or quasi-steady state. And so some replacement is done. So non-dimensionalized X or something. And then gamma W is rewritten as 2.16 equation here. And this is a circulation parameter. And we'll calculate WA. It's an induced velocity on the blade. So induced velocity on the blade here is W in Z direction. And again, this is WA can be calculated by the Biot-Savart law, and shown here. The first term is induced velocity from gamma A, so bound vorticity on the airfoil, the blade. It's an integration from the leading edge to the trailing edge. And the second integration is from the trailing edge to the infinity. That is an induced velocity from gamma W wake vortices. So those two vortices must be considered to calculate the induced velocity on the blade. And we use this 2.16 gamma W into here, and we can have this 2.17. So here we have gamma A. This is unknown parameter. And we changed the expression of the gamma W into this one. It's a circulation parameter. So this is an integral equation for the unknown gamma A. Okay. And this is in the very long time ago. It was analyzed by Professor Kuta and Professor Zengen, and Zengen N. We need N here, and we have Zengen's inverse formula. So from this equation, integral equation, we directly have the gamma A, explicit expression of gamma A shown here. Okay, 2.18. And so we can get gamma A, the explicit equation. But be careful. So in the right-hand side, there is an circulation parameter omega here. So it contains also gamma A. So it's not the free explicit expression of gamma A. So we have to calculate this circulation parameter in the other way. So then we proceed the integration calculation, and we have 2.19. And relationship, yes, this is an omega. Omega is expressed like this. So 2.19 is used into this one, and we derive 2.20 for circulation parameter omega. Okay. And here we have a first order and the zeroth order, the second kind Hankel function here. And Hankel function is yes, shown here. It's a combination of the first kind Bessel function and the second kind Bessel function. But in this expression, so we have WA here on the right-hand side. So if we use the boundary condition here, we can calculate this circulation parameter. And then we use this circulation parameter into the previous expression here, 2.19. And then in this process, we can get finally the gamma A, the value of gamma A successfully. So as written here, if WA bar is given based on the boundary condition, the unknown vorticity gamma A bar can be obtained from equation 2.19 and 2.20. Sorry. So we got gamma A, the value of gamma A. So then we'd like to have the pressure data or unsteady aerodynamic force on the blade. So pressure difference between upper and lower surface of an airfoil, it's delta PA, is related to the vorticity gamma A. So we'll calculate that relationship. So delta PA is calculated by the difference between upper surface pressure and lower surface pressure. Okay. And it's also harmonic. So from the equation of motion, it's equation 2.6, excuse me. From the equation of motion, we can derive the expression of pressure by this equation. Okay. And PU is here, and PL is here. So it's an upper surface, so 0 plus, and it's a lower surface, 0 minus. And the vorticity, gamma A, bar is related to the perturbation velocities on upper and lower surfaces. It's a perturbation velocity U prime on the upper surface and on the lower surface. Okay, the difference is gamma A. So we have this is again the equation of motion, and we can calculate delta PA by from these expressions. We can get delta PA like this, and here it's an upper surface potential and lower surface potential. The upper surface potential is here, shown here. So the integral of U prime from upstream position to X on the upper surface, and phi L is calculated by integration by this on the lower surface of the blade. So phi U minus phi L is calculated by this, and using this expression of gamma A, we can calculate it into this form. It's the integration of gamma A. So if we use this expression into this one here, finally we can get the delta PA expression by gamma A only here. So we could get gamma A, the value of gamma A. And if we use gamma A value here in this equation, we can calculate the pressure difference between the upper surface and lower surface. It's directly connected to the unsteady aerodynamic force on the blade. And if we use the 2.19 equation here, this one, gamma A, into 2.22 here, so we can calculate the pressure difference like this. So this is a final form of the pressure difference between upper surface and lower surface of a blade. Okay. And here we have a function lambda is expressed like this. And we also have ck, the function ck emerges here. So this function is called Theodosian function. This is given by this expression, Ck, is combination of the Hankel function. So we need to get this one. It's a function of the reduced frequency, and we put it into this one here. So as I will show later, this Theodosian function is then the function or correcting term from the quasi-steady state to the unsteady state. So it's directly connected to the unsteadiness of the flow field or the phenomenon. Okay, and Ck is drawn like this. This curve is Ck. This is an the horizontal axis is a real part of Ck, and the vertical axis is imaginary part. And if k equals 0, it's a quasi-steady state. The Ck has the value of 1.0. It's on the real axis. And then, the increasing, if increase the k, the frequency, this value changes along this curve like this. And this is a limit of the infinity. And the value is 0.5, also on the real axis. So this is some correction from steady state to the unsteady state. This is the meaning of the Ck Theodosian function. So we can calculate the pressure difference between upper surface and lower surface using WA. This is from the boundary condition of the blade. And lambda is calculated like this. And Ck comes from here. So this is the whole set of the extrapolation of delta PA. So we can calculate it by this method. And then, so this is a framework of the singularity method. But let us discuss, based on the theory, let us discuss the aerodynamic force acting on a two-dimensional oscillating rigid airfoil. Very simple case. So an airfoil is modeled as a 2-degree of freedom oscillation system of a rigid body. Yes, and the motion of the airfoil is expressed as a linear combination of the translational displacement of the point x here. Yeah, C over 2 multiplied by A. And HT is a displacement and positive in downward direction. Okay, it's displacement. And the pitching around the point here, it's an alpha. It's a positive in pitch up direction. So the displacement of the airfoil is expressed as this 2.226 ZA is minus H minus this one. It's a pitching motion. So accordingly, the WA is the velocity of the airfoil can be calculated by this. Okay. This is used as a boundary condition of the theory. So assuming a harmonic perturbation velocity as here, then equation 2.27 is divided by exponential I omega t. So WA x asterisk is shown here. We can calculate the boundary condition WA here. So, and we use this WA into the equation 2.23. The pressure difference can be calculated. Okay. And I'll skip the detailed formulation, but the result, I'll show the result. So please follow the formulation if you have time and interest. And the lift force L is calculated by the integration of the delta PA from leading edge to the trailing edge. And moment around the point X equal C by 2 half chord multiplied by A, and MA is the moment, is calculated by this expression. Okay, so the results is shown here. 2.30 is lift force, and 2.31 is moment. Okay, so it's a complicated expression, L and MA, and the component of the right-hand side, 2.30 and 2.31, broken down or categorized into 3 forces and 1 couple of forces. It's shown in the figure 2.4. Okay, so there are 3 forces by this arrow and 1 couple of force here. Okay. So we can understand these forces like the followings. So the first one is here, 2 pi rho u half chord ck multiplied by this one. It's a second term of the lift force on the right-hand side. This is a lift force determined by z component of the fluid velocity at 75% chord position. It comes from here. And the center of which is located at 25 chord position. It's an aerodynamic center. So this is the force shown by this arrow. It's working on this point. It's a first force. And the second force is here. We can have pi rho half chord squares. And this is an acceleration term. So it comes from here. This is a lift force expressed as a product of virtual mass and the acceleration at the 50% chord position here. So this is virtual mass or apparent mass or added mass. So Professor Maiti said it's added mass, but another name is apparent mass or virtual mass. That is a mass of fluid around the airfoil. So if the airfoil oscillated in the fluid, so because of the viscosity, this airfoil is followed by the air around the airfoil. So the mass is equivalent to this pi rho and multiplied by the square of the half chord. That is the virtual mass or apparent mass or added mass. And this is an acceleration. So this force is forcing at here 50% chord position. This one. And third one is this one. It's a lift force expressed as the product of the virtual mass and u alpha dot. And the center of which is located at 75% chord position. It comes from here. This one and this one. Lift force. And it's shown here, this one. So it's also related to the virtual mass here. And the fourth one is this one. It's a product of apparent inertial moment and the angular acceleration. It's a pitch down moment. So that is here shown. So we can categorize the resultant forces into these 4 kinds of forces. Okay. So this is the very simple case, the result of the very simple case of this oscillation model. Okay. And next, so it's a physical meaning of the Theodosian function. So in the case of translational motion only, we have the lift force shown here. And the first term is the apparent mass force. And the second one is damping force. And MA is expressed as this. So from 2.31, so found that the apparent mass force acts on 50% cold position, and the damping force acts on 25% cold position. So if the harmonic oscillation is slow, that is k nearly equals to 0, ck is 1 unity. And in this case, the damping force is here. It corresponds to the quasi-steady aerodynamic force in a translational motion. And damping force is described by a vector with a phase delay of 90 degrees from the displacement h. And k is non-zero. The damping force is multiplied by ck. So the function ck changes according to the change in k, as shown in the figure 2.2. Yes, this is an expression of the curve expression. Yes, it's Theodosian function. So if k is not 0, it changes to in this direction. Okay, and and the magnitude of the damping force becomes the absolute value of ck times bigger with increasing k. And the phase delays are 90 degrees plus theta. So theta is shown here in this figure 2.2. Theta is this angle from the horizontal axis. It's a real axis. This is theta. It's a phase lag of ck. So phase is delays 90 degree plus theta from the translational motion. So the phase delay is the largest at around k equal 0.2. And this phase delay has a critical influence on the Flutter characteristics of the airfoil. So this is damping force, and in the unsteady case, there is a phase lag of theta here. Okay, and this is a very, very important parameter for Flutter instability. And if so, k equals 0.2 is here. So this is its contact line is like here. So in this case, theta is the biggest, around 0.2 of k. Okay, so be careful to the Theodosian function. We need it essentially. Okay. Okay, this is the outline of the singularity method. And then we'll talk about Flutter. And the Flutter is an aeroelastical self-oscillation with fluid structure interaction, and consider single two-dimensional airfoil model with 2 degrees of freedom, shown in figure 3.1. And the mechanical damping is neglected here. Only the aerodynamic damping is considered. And the equation of motion of airfoil is written like this. So this expression is also shown by Professor Maiti on the Monday, and it's a similar one. But it's not, it's neglect the mechanical damping. Okay. And this is a lift, concerning lift, and translational displacement is h. And torsional displacement is alpha. It's on a moment expression. Okay. And yeah, and in the case of small oscillation, h is this one, and it's a harmonic motion, and alpha is here, shown here, and there is a phase lag phi. It's a phase difference between the bending translational motion and the torsional motion. And the unsteady lift and moment are expressed like this. And LH is the unsteady lift coefficient induced by the bending oscillation, and L alpha is an unsteady lift coefficient induced by the torsional oscillation. Torsional oscillation also induce the lift change. And MH is an unsteady moment coefficient induced by the bending motion, and M alpha is an unsteady moment coefficient induced by the torsional motion. So these coefficients are functions of reduced frequency K, and expressed as follows in uniform, incompressible, and inviscid flow. It's very simple expression. It's containing Ck here. And M is shown like here. So these are a function of reduced frequency, okay, mainly. And we need, every term we need Ck. And A is the coordinate of the elastic axis, and Ck denotes the Theodosian function. This is an approximate formula of the Theodosian function. Okay, it's very convenient. And aerodynamic work in a period of airfoil oscillation is shown here. It's R is a real part. The HR is the real part of the displacement. This is a moment. And it's integrated in one period. So if we use these above equations here, we can calculate it as 3.6. And here, suffix R and I denote the real part and the imaginary part respectively. Okay. So this is the work. Yes. And we consider this one for evaluating the Flutter instability. And this is its explanation is written here, but yes, I'll skip it. And for example, the steady aerodynamic force acts on the airfoil. So L is here, shown here, as I showed previously. We used this previously. And M equal L multiplied by BE. And the energy input is calculated as 3.8 here. So very simple expression. So again, this is a similar expression as in the morning session, of today's morning session. So when the aerodynamic center corresponds to the elastic axis, E equals 0. So this is eliminated. And in this case, the stability of the oscillation is summarized as follows. 1 degree of freedom, the bending oscillation, alpha 0 equals 0. So W is always negative, so it's stable. And torsional oscillation, H0 is equals 0, so it's neglected, eliminated. So W equal, and this is also 0, so W equals 0, always 0. It's a neutrally stable case. But in 2 degrees of freedom, H0 and alpha 0 is non-zero. And so we need to evaluate the value of this one and of this one. So if this value is larger than sine phi, W is negative, the stable case. But on the contrary, if the first time is smaller than sine phi, first term, not first term, sorry. This value is smaller than sine phi. W is positive, so it's negative damping Flutter. So for non-stalled singular, for 1 degree of freedom Flutter doesn't occur, as I showed previously. And a 2 degree of freedom Flutter can occur due to the interaction between bending and torsional oscillations. So the two natural modes are combined to become an oscillation of a common frequency omega by the aerodynamic force. So that is characteristics of the 2 degree of freedom oscillation, Flutter oscillation. Okay. And okay, so we'll skip these kind of things. And from the oscillating airfoil, the vortices are shed to wake surface in accordance with the change in the circulation around the airfoil. And the shed vortices from a vortex street with a wavelength of lambda the wake vortex street induces an upwash on the airfoil, and accordingly, unsteady aerodynamic force. The unsteady aerodynamic force has the following form. And this is then a general expression of the unsteady force. So it's important understanding. So F is composed of 3 terms. The first term is quasi-steady term. So CK is 0. And FW is the wake term. It's induced by wake vortices. And the third one, FM, is apparent inertial term. It's concerning the apparent mass. Okay? So we have 3 components of the unsteady aerodynamic force. Okay. So K is always important. And so for aerodynamic similarity, it's required that reduced frequency K is identical. So K is the ratio between representative length of airfoil and the wavelength of the wake vortex street. So this is very important. And hence, the reduced frequency is a parameter of unsteadiness and also simultaneously a parameter of aerodynamic similarity. And for mechanical similarity, the equality of the omega h over omega alpha, the frequency ratio, and the equality of the ratio of inertial force and external force, aerodynamic force, that is required for the mechanical similarity. So this parameter is written like this, and rewritten by K here. So this one, the first one term, m over pi rho b square, it's a mass ratio. It's called mass ratio. It's a ratio of the mass of the airfoil, it's a material, and the mass of fluid, it's air. Okay. So it's a very important parameter. But in the compressor or turbomachinery, usually this mass ratio is very big, and 100 over 100. So we can treat the airfoil as a solid one. But the problem is recently the mass ratio is reduced because for fan blade, the hollow airfoil is used, or composite materials used. So mass ratio is nowadays it's reducing. So sometimes we have to consider the effect of the low mass ratio. It means there is some modification of the oscillation mode due to aerodynamic force. That is a very complicated situation. Okay. So I'll explain some example at the last stage of this lecture. So yes, it's here. It's written in a cascade blades. The mass ratio of each blade is large, and the flutter is relatively unlikely to occur. However, we have to consider the interaction between blades and the cascade flutter can occur in the operating conditions. It's also possible to occur the 1 degree of freedom non-stall flutter in cascade because of the effect of the other blades. So that is the situation of the cascade flutter. And this is an expression of the cascade. So consider an annular cascade, including uniformly placed end blades with the same characteristics. The cascade is considered a multi-degrees of freedom oscillation system with n times degree of freedom compared with a single airfoil. So we assume that there is only the aerodynamic interaction between the blades. And the equation of motion for each blade is expressed as this one. Y is the displacement in the cascade direction. And it's an this is an equation of motion, and F is an aerodynamic force. And since the mass ratio of each blade is large, the blade can be assumed to oscillate at its natural frequency omega, and not affected by aerodynamic force. So the displacement yn is the nth blade. N is the blade number from 1 to n. And the displacement yn is written as this one. So it's an harmonic oscillation with frequency omega. Okay. And an is the oscillation amplitude of the blade number n. And aerodynamic force on the blade number n is induced by the other blades. So the expression here is n plus s blade affect n blade number n. So the aerodynamic force on the blade number n induced by the oscillation of blade number n plus s is denoted as here, f n plus s and n. So this is expressed like this. And Bs is called inference coefficient. And Bs indicates the strength of inference from the blade with distance s apart from the blade number n. Okay. And the overall aerodynamic force acting on the blade n is the summation of the effect of all blades here. So the summation from s equals 0 to n minus 1, f n plus s n is executed on Fn. So substituting these expressions in the equation of motion 3.9, we obtain here the ratio of amplitude of an plus s and an is exponential is beta. And beta is here, shown here. This is an IBPA, the interblade phase angle. So the cascade flutter occurs in the manner that each blade has a constant interblade phase angle, IBPA beta, and that all blades have a constant oscillation amplitude and mode. And the number of possible IBPA is n, the number of blades. The flutter velocity can be obtained for each IBPA, and the minimum velocity among those flutter velocities gives the flutter boundary. So we can select the IBPA at n sorts of IBPAs. But at each IBPA, we have a velocity, so flutter boundary. So the most dangerous case is the flutter boundary on that system. Okay. So, and we need to know the unsteady aerodynamic force Fn. And this is a main issue of from aerodynamic side, this one. So a lot of researches have been made to obtain it by theoretical analysis or experiments or CFD. So if we can have Fn, we calculate or we analyze the flutter instability. Okay. So let us proceed to the fundamental method of singularity analysis for cascade blades. So it's the same as the single blade. So we extend it to the cascade one. So there are many, many blades. So we include all the influence of the blades into one equation. But you know the fundamental framework already. So the singularity analysis method will be described for two-dimensional non-loaded linear cascade composed of flat plate blades. So analytical models, again, this is as a common model of the cascade, so a linear cascade. So a linear cascade composed of infinite number of flat plate blades in incompressible flow and inviscid flow with a uniform velocity u. So each blade is set at zero angle of attack in the flow without steady loading, executing small amplitude harmonic oscillation with an angular frequency of omega and IBPA of beta. So the potential, perturbation potential, is induced in the field, and this potential satisfies this Laplace equation. And the boundary condition is non-permeable condition on the braid surface and Kutta condition at the braid trailing edge. Okay. And so in this case, the oscillating braid surface is modeled by a vortex, one of the fundamental solutions of the Laplace equation 4.1. So vortex is one of the basic solution of the Laplace equation. So that is used as a singularity for this problem. So it's called gamma B. It's a bound vortex or bound vorticity. And Xi is local coordinate on the braid surface. And the change in the circulation around the braid is equivalent to the time variation of the bound vorticity, and the change in the bound vorticity generates the shed vortex from the trailing edge to the wake. So the shed vortex is called as free vortex or wake vortex, written as gamma W. So as shown here, there's gamma W on each braid. Okay. And the next step, the induced velocity on the braid surface by all bound vortices and wake vortices are calculated. So it's this one. So by introducing the boundary conditions on the braid surface, the distribution function of the bound vortice is determined, and the aerodynamic force on the braid is obtained from the distribution function. So this is the y component of the induced velocity on the central braid, number 0. So number 0 is the reference braid. So we calculate the induced velocity on this braid, and then we put the boundary condition on this surface. So Vsx0 is expressed like this. It's shown in the morning session also. So this again, it comes from the Biot-Savart law, and this is an induced velocity by gamma B, bound vortex. And the second term is an induced velocity by wake vortex. But here we must have the all braids. So M is the braid number. And the summation, this summation means that we include the inference from the all braids. And XM and YM is the coordinate of the each mth braid coordinate. So this is the distance between the vortex point and the reference point for induced velocity. Okay. So and theta is a stagger angle. So we can calculate Vs by this expression, and integration is on the surface for bound vorticity, braid surface, and integration is on the wake for the wake vorticity. Okay. So this expression is the same as for the single airfoil, but we include the inference of all braids here. Okay. So the framework is the same as for the single airfoil. The free vortex gamma W is shed from the trailing edge according to the time variation of the bound vorticity gamma B to fulfill the circulation conservation law. So the relationship between gamma W and gamma B is derived as this one. So gamma W is shed from gamma B. So this expression, relates the gamma B and gamma W. And we use 4.3 into 4.2. We can derive this expression of the induced velocity. So here we only have gamma B, here gamma B. So if we use a boundary condition on this Vs, we can calculate gamma B from this integral equation. It's a framework. So E is summation. Okay. So by introducing the amplitude of the braid oscillation velocity into the right-hand side of EQ4 4.4, the non-permeable boundary condition on the blade surface is satisfied. So we have to use the blade oscillation velocity as a boundary condition here. Okay. So through these processes, the integral equation to obtain the bound vortex gamma b is derived. Okay. So this is the integral equation for gamma b. But in this, in general case, we cannot have an analytical solution. So we have to do some computation for approximate solution. So if we get gamma b, we can calculate the aerodynamic force by this equation. And this unsteady aerodynamic force is expressed as a non-dimensional one, Cf. Is F divided by rho cu q. Q is the oscillation velocity of blade. And this is a converse value. So real part is CR, and the imaginary part is CI. Okay? And CR is the component in phase with the blade oscillation velocity, while the imaginary part CI is the component whose phase is 90 degrees advanced from CR. So real part corresponds to the aerodynamic exciting force, and the blade is excited when CR is positive. Okay? So we have to take care of CR. This is the sign of CR. So, and that is the framework. But if we compute in realistic case, it's there is several problems. It's a complicated situations. The integral equation 4.4 cannot be computed by analytical method in general. But for some simple cases, we have analytical solution like Zengen's formula. But in the general, we cannot use such kind of analytical solution. So we need to solve the equation numerically. So for numerical calculation, we can have two choices. The first one is that the one vortex distribution function is expanded with some appropriate series. So series expansion can be used. And the expansion coefficients are calculated as a solution of the algebraic simultaneous equations for the coefficients. And the second one is the unknown vortex points are distributed on the blade surface. It's a discrete method like CFD. And the algebraic simultaneous equations are derived for the unknown vorticity of each point. It's a panel method or something. So, but the first one is more sophisticated. And for the first method, we usually use the Groat series. It's a well-known series. And this is expressed like this. So Groat series satisfies the Kutta condition at the trailing edge, and the singularity at the leading edge is properly involved. So we use usually this one. And we expand in this equation, we expand gamma b by the Groat expression, Groat series. And the unknown is changed to the series coefficient. So that is easily integrated, and you can have matrix type equations. And for the second type, for the second method, on the other hand, the coordinate of the vortex point is replaced by here, and lambda is equally divided. So by this division, the vortex points are densely distributed near the leading and trailing edges. So this is also usable for calculation. And from this point, it's so only the mathematical treatment. So please read it afterwards. And the problem is here, from here. So equation 4.4, we look at equation 4.4. We have a singularity in the kernel function of these expressions. Okay, so this integral has a singularity at singularity of x 1 by x minus c. So c is an coordinate, the position of the vortex point, and x is the position of induced velocity we would like to calculate. So if the vortex point comes to the induced velocity evaluation point, the induced velocity is infinitely big, large. So that is a source of the singularity. So in this singularity, we use some special treatment. It's a mathematical treatment to eliminate the singularity. So I'll skip the detail, but it's a special treatment. It's usually used for the integral equation. So you can read the textbook of the integral equation. And then, so another problem is the summation. Yeah, here, this one. So this one is convergent summation, but the convergence is very slow. It's an 1 by x, yes, so term. So the convergence is very slow. So we usually transform this expression into the series of exponential function. So this treatment is, I think I wrote this one. Sorry. Yes, yeah, here. Yeah, the series sum is simplified by using the following relationship. So we can use this kind of series of exponential function instead of the original form. So I think there are two mathematically important treatments for solving this integral equation. But it's a very detailed point, so I don't touch the detail, but please look at the textbook of the integral equation. Okay, and finally, this example is shown here. This is calculated the case of k equals 0.2, and solidity is 1.0, and stagger angle is 45 degrees. It's plotted CR and CI are plotted here. It's a real part of the unsteady aerodynamic force and the imaginary part of the unsteady aerodynamic force. And from this is an IBPA scaled by here, but IBPA over 360 degrees. Okay, and CR is an exciting force. So if CR is positive, the flutter is unstable. So the flutter occurs. But in this case, all CR is negative, so it's a stable case. Only so non-loaded blade, and yeah, I wrote here. Yes, it's the oscillation is stable. So in the case of no steady loading, it's known that the 1 degree of freedom bending flutter doesn't occur. So that is corresponding to that knowledge. So also CI is plotted here. So we can have this kind of S-curve, like S-curve, as I showed you. So this is an example of the calculation. Okay. And in the previous case is the case without any steady loading, so no angle of attack. But if we can calculate the steadily loaded case, this method is also applicable for that case. So in that case, the blade surface is replaced by the combined vortices. One is a steady vortex corresponding to the steady loading, and the other is the unsteady vortex expressing the blade oscillation. In the previous case, we used only the unsteady vortex, But in the steady loaded case, we need to use steady vortex and unsteady vortex both. And be careful, we need to consider the additional unsteady vortex. So because steady vortex is oscillating, so it generates a new unsteady vortex. So original oscillation vortex, unsteady vortex, and the induced vortex induced by the oscillation of the steady vortex. So we have three kinds of vortices in the field. So that is very important point. But it's possible to calculate steady loading case. And also three-dimensional problem. For three-dimensional problem, it's also applicable to the three-dimensional problem. But I don't have any chart here, but in the three-dimensional case, there is a longitudinal vortex also exists in the flow field. And this longitudinal vortex has an axis in the flow direction. So it is okay, longitudinal vortex. So, we need to consider this longitudinal vortex also. And if the blade doesn't have the tip clearance, the all perturbation components can be expanded into the span-wise modes. So because there is no tip clearance, so it's continuous in the span-wise directions and wall and wall. So for instance, pressure has an cosine modes in span-wise direction, and velocity has sine modes in the span-wise direction. So we can expand all the perturbation parameters into these series. Okay, so so looking at the one expanded mode, this is two-dimensional. So the span-wise coordinate is eliminated. So we can calculate as a two-dimensional problem like the previous examples. And then after the two-dimensional calculation, we combine all the modes into three-dimensional modes. Okay, so that is relatively easy to calculate. But if there is tip clearance, it was my PhD work, and it's very complicated. And in that case, we need to use some kind of discrete type of calculation. So, for instance, it's used a vortex lattice method. So the airfoil is divided into the segments, and on each segment, each vortex singularity is placed, and then we can calculate this the strength of the vorticity discretely. That is possible, but it's very, very complicated and time-consuming. So I have idea. It's the last part here. I have ideas. Some continuous treatment might be possible, even for the case with tip clearance, and a steady loading can be neglected. So for this case, my idea is a new effective mode expansion in the span-wise direction might be possible. So I have idea to use wavelet transformation for this kind of problem, but I have not done yet. So you can do that in the near future. Okay. Okay. So this. So I'll finish the lecture on the singularity method by this. Thank you very much. And tomorrow.